circles or something. I don't remember. You guys will like this, okay? So we actually did one day over this. That day, one of our snow days, we had like 2 days, and I don't even remember what the snow days.
It was like a 6-day weekend.
Yes, okay, that day. So one of the days we did, I kind of like squeezed all 4 of these sections into one day. So we're gonna kind of go back because it was just super surface level. But that was all about what's called a transformation. So a transformation is kind of like the big idea, and then we're going to cover each of the little smaller ideas each day this week. So the first one is a translation. But let's talk first about a transformation. So when we talk about a transformation, there's 3 things that a transformation can do. So transformation of a geometric figure, it's a mapping that results in a change of either the position, the size, or the shape. So it's going to take this figure, like a square or a circle or a triangle, something like that, and it either changes its position, which just means its location, moves it from here to here. It can change the size, bigger, smaller, or it could move the points and turn its shape around. Now, some of the vocabulary, and we talked about this in that one super surface level day that we did. When we're talking about the original figure that you start with, that you're going to map to a different one, the original figure is called the pre-image. And the resulting figure is the image. So let's say you have this triangle and you want to make this triangle bigger. The original triangle would be called the pre-image, and then the bigger triangle that you made bigger would be called the image. How we're going to use the notation to show the difference between, well, this is the pre-image and this is the image, is we're going to use what's called prime notation. So if we have triangle ABC, instead of giving the image a brand new name like XYZ, we're just going to use prime notation. So if we have the pre-image is triangle ABC, the image we might call triangle A prime, B prime, C prime, which is noted by those apostrophes there. One of the things we're going to be interested in today is certain transformations. They are going to preserve distance and angle measures. So by distance, it means the distance between the vertices. So if you had a triangle from this vertex to this vertex, when you go from the pre-image to the image, that distance is going to be the same. And also the angle measure. So if you're looking at angle A prime in the image would be the same as in the pre-image. So if you have a transformation that does preserve the distance and angle measures, it is going to be what's called rigid motion. Rigid motion. In other words, if a transformation does appear to be a rigid motion transformation, it just means they're the same figure, same size of figure, they're the same shape, the same size, they didn't get bigger or smaller, they didn't change their shapes. You could cut both of them out, lay them on top of each other, they'd be the same shape. Okay, that's if it does preserve rigid motion. So one of the things you are going to be doing today is deciding, okay, I have my pre-image and I have my image. Does the transformation appear to be rigid motion? So if you look at this first one here, the black is the pre-image, that's what I started with, and the blue is going to be the image. Now we have a bunch of different types of transformations we're going to talk about today is just translations. For rigid motion, it doesn't have to be a specific type of transformation. It just means that if you could flip, rotate, move, twist, turn, other than make it bigger or smaller, okay, would it lay right on top of each other? And if you look at this pre-image and image, you couldn't just slide it over, but you could like flip it over, right? And it appears, it doesn't, oh yeah, it does say right here. The keyword there is appear, without actually taking out a ruler or a protractor. I mean, it looks like it'd be the same thing, right? It just flip over and lay right on top of the other one, right? So I would say yes, yeah, That one looks like it does. Remember, it has to preserve angle, measures, and distance. So if I look at this one, I have my pre-image, which is a square, and the image, which is a square. So it does preserve angle measures, because they're all 90. Does it preserve distance? Now, how you would know it doesn't preserve distance? That side, if it's rigid motion, should measure the same as that side. Does not, right? It definitely got bigger. So that one would be a no. Okay, so now kind of getting specifically into the type of transformation we're going to talk about today is we're going to talk about translations. So a translation is a transformation that takes every single point in the pre-image and maps it the same distance and the same direction to the image. So in other words, if I were to take, like in this one here, point A, and I map it this far and get to A prime, if this is a translation, when I take B, I am going to map B prime the exact same distance and the exact same direction to get to B prime. And then I'll do the same thing with C. If I start with C, I should go the exact same direction, the exact same distance to get to C prime. So all of those lines should be parallel and should measure the same. Okay? So some properties with translations that are going to be helpful. First thing, some notation. We talked a little bit about the prime notation, but whenever we're talking about these transformations, it's technically a function. So to show the notation here, we are going to use function notation, which we haven't talked about a lot this year. But if you remember from last year, function notation looks something like this usually. It's an f of x equals, and then there was some kind of rule, okay? But if you remember f of x, f was the name of the function. It's not a variable, it's the name of the function. And x was kind of like what you plug into your function, what you're using the rule for, okay? So what the function notation is going to look like for translations is you're going to use capital T, the name of the function, the translation, okay, capital T, and I'm actually going to add something in here that I didn't do last hour, okay? Down here is going to be our rule, and we'll talk about that down here in the second example here, but it's going to be in like these little arrows, okay? It's going to be the transformation of triangle ABC. The transformation of triangle ABC is going to map to triangle A prime, B prime, C prime. So when you see this notation here, remember T, that's the name of the function. That's how you know it's going to be a translation. Tomorrow when we talk about reflections, it's going to be an R, okay? And then in the little arrows down there, that's going to be our rule. And then this is the figure that you're translating. And when you translate triangle ABC, you get triangle A prime, B prime, C prime. That's kind of in words what all of that means. Now, these specific properties that we can apply whenever I do translate triangle ABC, and we talked about some of them. A prime. So A prime, those are 2 points. A is a point, A prime is a point. So A prime is the segment between A and A prime. Since I don't have a line over top, going back to all of this vocabulary notation we've been talking about all year, that's the distance between A and A prime. So the distance between A and A prime is going to be same as B prime and the same as C prime. It just means that these 3 lines that I drew here, they're all going to measure the same. But here's the thing. You could have 3 lines. You could have A, B, and C going the same distance, but not necessarily the same direction. If it's a translation, they need to go the same direction. So another thing that is preserved, or another thing that's true whenever you have a translation, is that these segments A, B, in the original figure is the same as A prime, B prime, which just means that this measures the same as this. That's going to guarantee that A prime, and B prime are going in the same direction. And it's also going to be true for BC is equal to B prime, C prime, and AC equals A prime, C prime. And almost in a way unnecessary to even point out, but kind of good to know as well, the corresponding side lengths are equal, the corresponding angle measures are also equal. So the measure of angle A equals the measure of angle A prime. The measure of angle B equals the measure of angle B prime, and the measure of angle C equals the measure of angle C prime. So all of the corresponding angles are congruent, all of the corresponding side lengths are congruent, same distance, same direction. So if I were to ask you, is a translation rigid motion? Yeah. Preserves distance, because they're all moving the same distance, and direction. Okay. All right, now one of the things we're going to be doing today is actually translating some images. So this is that notation that we were talking about. It says, what are the vertices of, this is the transformation of triangle PQR. So it's drawn here for me. This right here is my rule. So you see how it has the little arrows. It says -2, -5. Your rule down here, if you see something like this, is going to be an X, Y rule. Meaning that the first number tells you how you are going to move along the x-axis. So since it's -2, it means you are going to move left 2 on the x-axis. And then since it says -5 on the y-axis, you're going to move down 5 on the y-axis. Now, if you're just drawing the picture, you could just take each one of these points, right? If you were going to translate triangle PQR, you could take point P and move it left 2 and down 5. That's actually what you're going to be doing with the with the translation. But what I want to know is I want to know what the vertices are. So I actually want to know the actual points. So instead of actually translating them, we're going to write them out. So what I'm going to do, we're going to get used to this notation here. We are going to translate P. We're going to translate point P. When I translate point P, it is going to map to point P prime. Now to get P prime, I need to take point P, which is at the point 2, 1. And like I said, my rule says I need to go left 2 and down 5. So if you wanted to, you could go left 2, down 5, but it goes off the graph, so you'd have to kind of count. Another way to think about it, if you go left 2, where would you be at on your x-axis? 0. And if you go down 5, -4. Subtract 2, subtract 5 would be at 0, -4. So P prime would be at 0, -4. We can do the same thing if we translate point Q. Okay, I first need to know where point Q is, and it is at 3, 3, which means Q prime would be left 2, down 5. So left 2 would be at 1, down 5 would be at, -2, -5, so we'd be at 1, -2. And then we'll do the same thing. We will translate point R to get R prime. Well, point R is at -1, 3. So if I do the same thing, my rule says -2, -5. Where would R prime be at? -3, -2. Now this specific example, it doesn't tell me to graph them. In your homework, if it tells you to graph it, you would need to draw a graph and graph these points. But for this one, it just wants the vertices. Okay. let's get this glued into, I'm gonna need some help with page numbers, I already forgot from last class. 80, oops. 79 is what I was, 79. And so this will be glued onto page 81. This is section 9.1, and it is a translation. Okay, so pretty simple day today. I think I guess I'll let you guys be the judge of that. One of the things you're going to be doing is going to be deciding whether keyword here, appears to be rigid motion. We're not going to get out a ruler. We're not going to get out a protractor. We're just going to kind of look and say, yeah, it looks like it appears to be rigid motion. So remember the two things. If it is rigid motion, it has to preserve angle measures and distance between the vertices. So for this first one, I have my pre-image, which is this solid triangle here. And remember, it can flip, it can turn. It really kind of the big thing. It can't get bigger or smaller, or kind of like move the points around. So if I take this pre-image and I were to map it to this image, if it preserves the angle measures, you should be able to match up the corresponding angles. So if it does preserve rigid motion, I should be able to tell, honestly, pretty easily which angle corresponds with that one there. Do you think we see one?
No.
Where would it be at? Yeah, that's right there, I think. I think those kind of go together. And then there's your right angle, and then that right angle, and then that one there, and that one there. So, I mean, it appears as those angle measures are congruent, that they look like they correspond. But I'd also need to make sure that the side lengths appear to be the same as well. So, like, if this is a right triangle, I don't know for sure if it is, but that hypotenuse should look like it's about the same size, which I think it does. That bottom side with that bottom side, yeah. I'd say that those are probably rigid motions. We'd say yes. Now, if I look at the second one, this one, I mean, I kind of had to look at it for a little bit.
No.
I mean, right, you think, like, if I were to do, like, maybe that one and this one, so it's kind of a shorter side.
Yeah, but the side is long.
Yeah, I know, like, it'd have to be one of these two. I mean, I couldn't figure out a way to, right, and once again, keyword here is appears.
I don't think
It does. It's the same.
Right, so if you did flip it upside down and kind of move it, then you could say, well, maybe this side, but that looks longer than that, doesn't it?
yeah.
Right.
You have to rotate it 180 degrees from the center point.
And even if we did rotate it 180 degrees, this would be this one, right? And to me, that looks longer.
Yeah.
Okay, yes.
Wouldn't that one actually be the one that it's like opposite from?
I don't think so. I think if you rotated it 180 degrees, that would flip up here and you'd be on the top left there.
Maybe like feel like it's more like bisected by the other one.
I don't think, regardless, however you rotate it
They are
around.
not the same.
Not the same.
Yeah, regardless, however, okay, here, you want to do this?
Okay.
Take your fingers, right? If it was the same, you should have a one that measures that, okay? There's not a side on this figure that measures that long.
Yes.
There you go.
People, they're fine.
There you go. If it does preserve distance, you should have a side this long, and there's not any of those that are that long. Very
See
good.
that, Leo? They're not the same.
No, Leo. Okay,
You're wrong.
all right. Okay, so next thing, we have this diagram. So we've got this, it kind of appears to be a parallelogram here. It is already, has a transformation applied to it. So we have the solid figure is the pre-image, the dashed figure is the image. We want to first choose an angle or point. Going to be the same thing, right? Because if you look at R is a point and an angle, so it doesn't matter. But we're going to choose an angle or point for the pre-image, name its image, and then we're going to list all of the pairs of corresponding sides. So let's start by picking an angle or point from the pre-image.
T.
T. So if I'm going to talk about T, angle T, point T from the pre-image, what is the image of point T. T prime. Easy enough. And you can pick any one of those and they would be fine. But now I want to list all the corresponding sides. So let's pick a side from the pre-image.
UR.
UR. And UR is mapped to U prime, R prime. And we're just going to do that with all of them. So then we could do RS, mapped to R prime, S prime. We have ST, mapped to S prime, T prime. And then TU, mapped to T prime, prime. Got any issues with that, Leo?
No.
Okay, good. Okay, now let's actually do some translating here. So I would say probably the most difficult part about today is just the notation because it's new. But once you get the hang of it, not too bad. So what we have here, we have triangle ABC. If you look at the rule here, we are going to translate triangle ABC according to this rule right here. Now, with this rule right here, remember the rule is always x, comma, y. It tells you do this with the x coordinates, do this with the y coordinates. So if my x rule is -2, what does that mean?
Down 2.
Eh,
Left 2.
Left 2, right? X, we're going to go left 2. And if my y coordinate is 3,
And up 3.
up 3. Now, read the directions, because it really doesn't say I have to say what the vertices are. So for this one, it might be easier just to take each point and translate it left 2 and up 3. So if I take A and I go left 2 and up 3, I'd have A prime right there. And if I take B and go left 2 and up 3, B prime would be right there. And then if I take C and go left 2 and up 3, C prime would be right there. So you have your image. Alright, and then lastly, we're going to go the opposite way. We are going to write a rule for the translation. Now, your rules should look like this. I want them in function notation. The only difference on these ones, your triangles and then your quadrilateral, they are labeled and we could actually name them, but the ones when you guys get to your homework, they're not going to be labeled. It's just going to be a triangle without vertices labeled or a line without vertices labeled. So I'll show you how you're going to change your rules to do that whenever you get to your homework. So to start off, okay, the function notation, we are going to translate. We're going to have our rule down here. We'll get to that in just a second. And if we want to be really, really specific here, we are going to translate your pre-image. So my pre-image is triangle ABC. When you get to your homework, it's not going to be labeled A, B, and C. It's just going to be a triangle. So what you'll need to change is you're going to say translate. You're going to have your rule. And you're just going to say x, comma, y, which just means you're going to translate according to this rule every x and every y this way. So if it doesn't have labels, you'll just do this. In this one, we can say triangle ABC. So if I want to figure out how I'm going to translate, let's look at how we go from A to A prime. So you always want to do your x shift first. So how are you moving along the x-axis? 2 to the right. So a positive 2. And then for the vertical shift, what are we doing? Down 5, negative 5. So that would be your rule right there. Once again, when you get to your homework, instead of triangle ABC, it would just be x, comma, y. Okay, then let's do this one here. So once again, we are going to translate. We'll figure out the rule here in just a second. When you get to your homework, you would just open a set of parentheses and say x, comma, y. But for this one, it's a quadrilateral, so we could actually name it WXYC. And you really just need to look at one point, because since it's a translation, we know they're all moving in the same distance in the same direction. So if we start with maybe x, I need to figure out first, okay, you have to go x first. Horizontally, how do you get from x to x prime? From x to x prime. From x to x prime. 5 to the right.
Yeah. That way.
Okay, wait, wait, touch that your left, right? Yeah.
Yeah.
Okay. Anyway, right 5.
5.
And then on your y-axis,
Up 5.
up 5. So 5, 5.